So in this video, we're going to be learning at drag force and terminal velocity. I'm not going to go through all the learning intentions, but you need to be explain and describe the following situations. So first things first is when a body moves through a medium, such as air, then the body experiences a drag force that opposes the motion of the body. So we're going to look at projectiles. So we're chucking a projectile up into the air. And so if it's chucked up on a diagonal or an angle, the force is going to be acting directly opposite. So it's going to be opposing the motion of the projectile. And so that force is going to act in both. That force opposing that drag force is going to have a horizontal and a vertical component of drag force. And so it's going to affect the vertical and horizontal components of velocity. So far, all the situations we've looked at have only been counting for gravity. So all your calculations will only ever account for, will say that the effects of air resistance is negligible. But you do need to be able to describe and explain the effect that air resistance or drag force does have on bodies moving through a medium. So you need to be able to describe and explain the effects of air resistance on the vertical and horizontal components of velocity, the maximum height, and the range of the projectile. Remember, range is just the horizontal displacement. So basically, the magnitude of the horizontal component of velocity reduces as time. So if you're chucking a projectile up into the air, the drag force is always opposing it. So on the way up, it's opposing it. If it was launched at an angle, it's opposing it at an angle, but it's going to have a horizontal component. So that force is opposing the motion, and it's going to be decelerating the object. So the horizontal component of velocity is going to be reducing constantly with time, as you can see here. So in red, we have the horizontal component of velocity with air resistance or drag force. So it's reducing over time. So basically, it's going to have no horizontal component of velocity towards the end of its motion, or minimal. It's just going to keep reducing. Now, when you chuck a projectile up in the air, so the force opposes the motion. So if you chuck it into the air, the force is acting directly opposite. So on the way up, as the projectile goes up into the air, the force due to drag is actually decelerating the object. So the vertical component of velocity is decreasing. So it's decreasing faster though, because there is a drag force acting opposite the motion. So this drag force is reducing the vertical component of velocity quicker. So it's actually, what's going to happen is it's going to reach its max height in a shorter amount of time compared to no air resistance. So it reaches its max height in a shorter amount of time. But on the way down, so now you've got an object falling. See, the object is falling, and the drag force is actually acting opposite. So it's falling, and the drag force is acting up. So on the way up, the vertical component of velocity so the acceleration of the vertical component is actually reduced on the way down. So it actually takes longer to get to a faster speed. So on the way down, it takes a longer amount of time. So it doesn't actually get as quick on the way down because you have that force opposing its motion. And so anyway, what happens is basically the range of the projectile is reduced because range is the horizontal component of velocity multiplied by the time of flight. So on the way up, the time of flight is decreased because the vertical component of velocity is being opposed. So the time of flight is decreased on the way up. Now, actually something funny happens, and I think I explain it on the way down, so I might not talk about time of flight. But the time of flight actually slightly increases on the way down because you have a force opposing it. So it actually takes longer for it to hit the ground. So due to air resistance, the time to reach its peak is reduced because of the force due to drag caused by the air resistance. But on the way down, that air resistance is actually opposing it falling. So the time of flight on the way down is actually a little bit longer. But overall, the time of flight is reduced. And because the time of flight is reduced and the horizontal component of velocity is reduced, the range of the projectile is reduced. And on the way up, the time of flight is reduced, so the maximum height reached is smaller. And basically what it results in is not that perfect parabolic motion, but more like this. This is a little bit overly exaggerated, but yeah, it'd go like this and then down. So it's definitely not symmetrical because that horizontal component of velocity, it continues to reduce with time. Now, you need to describe and explain the effects of air resistance on the time for a projectile to reach the maximum height or to fall from the maximum height. So as that projectile is reaching the maximum height, the drag force due to air resistance acts opposite, causing the projectile to reach its max height in a smaller amount of time. And then on the way down, the air resistance is now acting opposite, so upwards, and that's opposing the motion. This actually increases the time taken to descend from its max height, which is what I explained before. However, because the time of flight was reduced on the way up, it's still going to reduce in a net overall reduced time of flight. Now, this is a super important formula that is not on your formula sheet, but it's easy to remember and it helps you remember the following things. And we're going to use it in our first practical summative experiment. So it is an important formula to note down. So basically what it is that the force due to drag depends on the following 4 factors. So force due to drag is directly proportional to density. So this we read as rho. It's a P, but it's the Greek symbol for rho, and it signifies density. And so force due to drag is directly proportional to the density of an object. So basically the density of a medium that the object is in. So the more dense the medium, the more particles, the more opportunities for those particles to apply a force. So basically air is less dense, so it's going to have a smaller drag force because they're directly proportional, but water is going to be more dense, so it's going to have a larger force due to drag, which we've all experienced in our everyday life. It's a lot easier to walk through air than it is to walk through water, much larger drag force from water. Now, the drag force is actually directly proportional to speed squared. You don't need to know why it's speed squared, but it is directly proportional to speed squared. So basically, the faster something's moving, the larger the drag force is going to be on the object in that medium. The cross-sectional area. So the cross-sectional area is basically just that area that is directly perpendicular. So that frontal area across there that is directly perpendicular to the motion of travel. So if you're throwing a ball through the air, it's throwing it purely horizontal, that's going to be the cross-sectional area. So the diameter of the ball will give you the cross-sectional area, that frontal area perpendicular to the motion of travel, to the direction of travel. So basically, the larger the cross-sectional area, the more particles there will be that are going to exert a force on the object, and hence the larger the drag force. The drag force is directly proportional to the cross-sectional area, directly proportional to the density, and directly proportional to the speed squared. And finally, our last symbol, CD, that's the coefficient of drag. And the coefficient of drag is a number that is based upon the aerodynamic shape of the object. So the more streamlined the object, the smaller the coefficient of drag. So something super, super streamlined, the air goes over nicely and doesn't have much impact on the object. It's going to have a very low coefficient of drag. So that's going to significantly reduce the drag force. Things that are more bulky, things like the cube, horrendous, 1.05, cylinder, 0.82, etc., etc. You don't need to memorize any of these. You just need to know that based on the aerodynamic shape, that will affect the force due to drag acting on the body. Now, finally, there's a couple of explanations. I'm not going to read exactly what I've written here, but basically you need to be able to explain terminal velocity, and this occurs when the magnitude of the drag force results in zero net force on the moving body, and you need to use this idea to describe situations such as skydiving and the max speed of race cars where terminal velocity is actually achieved. So to help us explain this, we're going to look at this diagram of this skydiver. As he jumps out of the helicopter, initially he just has his force due to gravity. Now, as soon as he starts falling through the air, the force due to drag from air particles is opposing the skydiver's motion. Now, remember, as he falls, he's accelerating downwards due to gravity. and what's happening is he is gaining speed. And if we can recall from the previous slide, the force due to gravity is directly proportional to the speed squared. So as the skydiver accelerates, the skydiver gets faster, higher speed, higher force due to drag. So as he's falling, his force due to drag is increasing until it gets to a point where the force due to drag is equal and opposite to the force due to gravity. At this point in time, there is no net force on the skydiver, so he is not undergoing any acceleration because there's no net forces. No acceleration, therefore he's not increasing in speed, and he has reached his maximum speed, and that maximum speed is known as terminal velocity. Likewise, we can apply it to a race car. Race car has a few more forces going on. So obviously there's, we have the friction between the tires opposing the motion. We have the gravitational force and we have the normal force opposing that. They're balanced. But we have the driving force from the motor and we have the drag force due to air resistance opposing the motion of the vehicle. And very much the same thing happens. As the car accelerates, it gets faster, and as it gets faster, the drag force opposing it gets larger because of speed, and eventually it keeps accelerating, and eventually it will reach a point where the driving force from the engine is equal and opposite to the force due to air resistance, and at that point in time the net force on the car will be zero, and hence it can no longer accelerate and it can't increase in speed, and therefore will have reached its terminal velocity. So I want you guys to now have a go at these questions in the textbook. They're mostly primarily around looking at drag force. Let me know if you have any issues with questions. Thank you.